This object is at the heart of understanding relativity. It fully describes spacetime geometry, including its curvature. It helps us compute with absurd levels of precision how this curvature affects time, without which GPS satellites and Google Maps wouldn't work. It helped us discover and correctly model black holes and event horizons, gravitational waves, and even the expansion of the universe itself. I kid you not, it's that powerful. It's called the metric tensor. But what exactly is it? When I tried to read about it, all I got were these vague definitions, and that it can be written as a giant matrix with a lot of components, and that it's covariant, whatever that means. And it's used in this particular formula, which has a lot of mu's and nu's. Yeah, none of that made any intuitive sense to me until now. After going through a lot of resources, I think I finally have some intuition behind the math of relativity. And boy, oh boy, it's so cool, and I'm super excited to share that with you. So in this video, we're gonna pretend we don't know anything about metric whatever, and like always, rediscover everything from scratch, step by step, intuitively. So if you're ready for this, let's begin. So Einstein, where do we start? And Einstein says, let's get right to it. Let's start with a ridiculously simple question. Can you find the distance between these two houses? And I say, sure. I mean, horizontally, they are 3 units apart, and vertically, they are 4 units apart. So from Pythagoras' theorem, they must be 5 units apart. But Einstein says, Mahesh, what's the physical distance in kilometers? And I say, well, for that, you need to tell me how big a unit is. For example, if 1 unit is 1 kilometer, then the distance is going to be 5 kilometers. And Einstein says, exactly, Mahesh, this is the metric tensor. I mean, there is a small nuance to it, which we'll get back to later. But at the heart of it, metric tensor is a mathematical object that converts from arbitrary coordinates to real physical distances. And I say, that's it? That's what a metric is basically a conversion factor. Then why do we call it a tensor and make a big deal out of it? Why does it have all of these components? Mahesh, why don't we shrink the grid to half its size? Now look, the horizontal distance is, instead of 3 units, 6 units, and the vertical distance has gone from 4 to 8 units, which means, according to Pythagoras, this distance is now 10 units. Does that mean that the distance between the houses has changed? And I say, of course not. Because look, now 1 unit is half a kilometer. So if we multiply by the metric, then we get back the same answer. And Einstein says, look, this means when we shrunk the grid, the metric transformed in such a way that the physical distance remained invariant. And that lights up a bulb in my head, because that's exactly what a tensor does. That's the core feature of a tensor. Its core feature is that when the coordinates transform, the tensor transforms in such a way that the underlying physical quantity remains invariant. So that's why it makes sense to call the metric a tensor. Beautiful, right? Okay, now that we know that the metric is a tensor, the next obvious question we have should be, Einstein, what's the rank of this metric? And Einstein says, Mahesh, for that, tell me this. How many numbers do you think you need to fully represent the metric? And I say, well, just 1 number, right? Like we have shown over here. And Einstein smiles and says, well, Mahesh, that's the case if you're using a square grid. But what if you're using a rectangular grid? And at first, I'm like, why would anybody use a rectangular grid like this? And Einstein says, we'll get back to that. But now, how many numbers do you need? And I say, yeah, well, now 1 number is not enough. Now we need 2 numbers. 1 number to represent how big the unit is in the horizontal, another number to represent how big the unit is in the vertical. So right, we need 2 numbers. And now, Mahesh, can you compute the distances 1 more time to just confirm we get the same answer? All right, let's do this. So in this new grid, we have 1, 2, 3, 6 units horizontally, but still 4 units vertically. Ooh, that means I cannot directly use Pythagoras because they don't have the same units. I better first multiply with the metric, and now I get 3 kilometers, 4 kilometers, so obviously this will be 5 kilometers. So now if I use the Pythagoras theorem, the hypotenuse square equals the base squared plus the opposite side squared, giving us 5 kilometers. So Einstein says, look, Mahesh, this means when you're using a rectangular grid, you can no longer directly use Pythagoras. You need to have some coefficients in front that represents the scaling factor. It tells you how the different scales are for horizontal and vertical. Here, the scaling factor is half square, which is 0.2 0.25, and here the scaling factor is just 1. So remember that we said there was a nuance over here? Well, it's these numbers that are the components of the metric tensor, not these, the square of those values, because it's the squares that become the direct coefficient for the x square and the y square terms. Which means we can now generalize Pythagoras' theorem for rectangular grid. So all we have to do is add coefficients in front of x squared and y squared. These are the scaling factors. Again, these are the components of the metric tensor. And I ask, well, wait a second, why do you call it gxx and not just gx? Einstein says, well, that's because this is the coefficient of x squared term, x times x, and this is the coefficient of y squared term. Now at this point, I need to apologize. See, I should have actually written it as delta x and delta y, because remember, these represent displacements, not coordinates. But I forgot about it, and for the rest of the presentation, I've just written it as x and y. So for the rest of the video, whenever you see x, y, or z for that matter, remember it's actually displacements, not coordinates, okay? End of apology. All right, so this means we need two numbers to fully represent the metric tensor, right? And Einstein says, oh, Mahesh, that's true if we are dealing with axes that are always perpendicular. But what if the axes themselves are skewed? Like, oh no. So Mahesh, do you think the formula still works in this coordinates? And I say, well, no, because we no longer have a right angle triangle. But it's nothing we cannot handle actually, because we can always make constructions and complete the right angle triangle. So let's call this as x and y and forget about scaling for a second. And then we'll realize we've tackled this while doing vector addition in high school. What we should do is we should to complete this triangle. And then if this angle is theta, then the base becomes y cos theta and the opposite side becomes y sine theta. And look, now I can compute the hypotenuse. So the hypotenuse squared becomes the base squared plus the opposite side squared. And so now if I simplify, I get this. And since sine squared theta plus cos squared theta is just 1, I can write this as y squared. And there you have it. And Einstein says, perfect. Now all we have to do is make this a little bit more elegant. How shall we do that? Well, first of all, you have this 2xy cos theta over here. Well, we can write this as xy cos theta plus yx cos theta. And I ask why? Well, because there's a nice ring to it, right? I mean, you have x squared term, then you have an xy, then you have the yx, and there's the y squared. So it's just beautiful, okay? But now if we add back the scaling factor, can you imagine what the general formula looks like? Well, it's going to be some coefficient times x squared plus some coefficient times xy plus some coefficient times yx plus some coefficient times y squared, which means we can write the most general formula like this. And by the way, these two coefficients, as you can see, are exactly the same thing. It's just written that way so it looks beautiful and symmetric. And while we're at it, the last elegance we can do is, instead of writing as x squared, we can just write as x times x and y times y. And boy, oh boy, look at this. The most general form of distance formula that will work in any coordinate system, written elegantly. Isn't that amazing? Anyways, look Mahesh, these four coefficients now become the components of the metric tensor. These two values tells you how much the x and the y-axis are scaling, and these two, which are equal, they tell you the angle between the x and y. So you need a total of 4 numbers in general to fully represent the metric in 2 dimensions. And I say, well, actually, it's only 3 numbers, right? The 4th one is the same. And yeah, 3 unique numbers, the 4th one is redundant. Remember, these two are exactly the same. It's written just for the sake of symmetry. So if you write it as a matrix, the matrix should be diagonally symmetric. For example, these are the values that you can have. So look, these 2 numbers should always be the same. And if these numbers become 0, that means the grid is perpendicular. We get back our rectangular grid. And if these 2 numbers are 1, well, we get back our square grid. We get back our Pythagoras theorem. So this is the simplest metric that you can think about. But anyways, this is what the metric looks like in 2 dimensions. Mahesh, what do you think the metric looks like in 3 dimensions? How many total numbers do we need and how many of them are unique? And I say, well, we can just extend this, right? We can just write a z over here and we get a total of 9 terms. Now, xx, yy, and zz, they represent the scaling in x, y, and z axis. And these terms represent the angle between xy and yz and zx. And of course, these 3 terms must be redundant with these 3 terms. That means in total, we have only 6 unique terms. And Einstein says, perfect. That's exactly right. And look, because we have written it so elegantly, it's easy to write the whole distance formula in 3 dimensions. It's going to be x into x times gxx, x into y times gxy, x into z times gxz, and so on and so forth. So that's why we write it so elegantly. So beautiful, isn't it? So Mahesh, can you now tell what the rank of the metric tensor is? And I say, well, okay, in 2 dimensions, the metric has 4 components, 2 squared. In 3 dimensions, it has 9 components, so 3 squared. In n dimensions, it'll have n squared components. So that square, that represents the rank. So it must be a rank 2 tensor. And of course, another way to see it is that there are 2 index to represent the tensor. So it's a rank 2 tensor. And Einstein says, perfect, its metric tensor is rank 2. But wait. Now I have a question. Actually, a really silly question. Einstein, how do I write this in n dimensions? I mean, notation-wise, because we have x, y, z, and then what, right? And Einstein says, Mahesh, that's not a silly question at all. Notations are a big deal. So let's look at how we do this. First thing, because we want to write this in n dimensions, instead of writing it as x, y, and z, we will write it as x1, x2, and x3. That's how we'll represent our dimensions, okay? So that's the first change we will do. And the moment we do that, we can now, instead of writing as gxx and gxy, we can write as g11, g12, g13, and so on and so forth. And the beauty is, Mahesh, look, we can now write this as a summation, isn't it? We can write this as summation of g, and we can use some letters to represent the index over here, and the indices will run from 1 to n, where n represents the dimension. So let's write it this way. So s square is the summation, and we usually like to use Greek letters for the index, so mu and nu, that's where the mu and nu comes from, 1 to n, and we can write it as g mu nu and x mu times x nu. Beautiful! That's the notation we can write and extend this to n dimensions. But now, just when everything is going really well, everything's starting to make perfect sense, Einstein does something very weird to me. He raises the indices on the displacement terms. Einstein, buddy, what did you just do? Why do we have x squared and x cubed? Where did they come from? And Einstein says, Mahesh, no, these are not powers. There are no exponents over here. These are still just indices, but instead of writing as a subscript, we write them as a superscript. And I say, why? Well, Einstein says, remember when we shrunk the grid to half its size, the metric also became half. And when we blow up the grid to twice the size, the metric also transforms to become double. So look, the metric changes in the same way as the grid. It co-varies with the grid. And so we call such tensors covariant tensors. Covariant tensors are the ones that vary in the same way as the grid. In contrast, if you look at the displacement vectors, when the grid shrunk to half its size, they became double. And if the grid becomes double in size, they became half, which means they vary in the opposite way as the grid varies. And so we call such tensors or such vectors contravariant tensors or contravariant vectors. Contravariant means these are the tensors or vectors that change in the opposite way as the grid changes. And the convention that we have adopted is for covariant tensors, we use the index as a subscript like usual. But for contravariant ones, the ones that vary in the opposite way, we'll choose the opposite convention. We'll use them as superscripts. It's just a convention. And so if we go back to our distance formula, we can immediately look at the index and say that, hey, this is a covariant term, and these two are contravariant because they have superscripts. And because you're multiplying a covariant with a contravariant, we end up with invariant distance. That's what makes the distance invariant. It's beautiful, if you ask me. And finally, because we know it's a summation, let's just get rid of the summation term and keep it clean. And boom, there you have it. Beautiful, isn't it? I mean, I am not much of a notation guy, but I'm a sucker for elegance, and this is so elegant. So that's it. This is the most general form of the distance formula, right? And Einstein smiles and says, no, there's one last generalization left. Mahesh, what if you use a grid that looks like this? Oh my God, this is such a mess. Why would anybody use a grid like this? I know, we'll get to that later on. But anyways, over here, oh my God, the units are changing everywhere. The angles are changing everywhere. Ooh, this means the metric is changing everywhere. At every point, we have a different metric, which means we now have a metric field. So how do you calculate the distance from here to here if the metric itself varies? Well, we can break it into small parts. We can zoom into small sections, and if the parts are very small, we can approximate the metric to be constant in that particular small section, and then use that metric to calculate the distances of those tiny parts. In other words, this formula in general can only be applied to small patches of space. This is a differential formula. So I should have called it as the small differential element square. And these are small differential x and y, or coordinate terms, displacement terms. This means in general, if we are calculating it, we have to add up all these individual elements, which means we have to integrate it. This is it in its full glory, the most general way to calculate distances. And we discovered it all ourselves just by using Pythagoras. I mean, imagine how teary-eyed Pythagoras would be if he knew that we could generalize his formula for n dimensions and make it work for abstract coordinates. Oh my God, that is amazing. And what's more amazing is that we can discover a lot of concepts just like this from scratch by using Brilliant.org, the sponsor of this video. I love Brilliant, and I keep recommending it because you can start becoming a better thinker for free. Like in my videos, it also takes a discovery approach with thousands of hands-on interactive lessons in math, science, programming, data analysis, and even AI. You're not just watching a passive video, you have to interact with it. You are forced to reason, you are challenged. And these lessons are highly focused, and they help you gain a deep intuition. And this is what is needed to help you level up and master the foundational skills. And I think this is the most effective way to learn anything. For example, if you've ever wondered how computers really work at the most fundamental level, check out their brand new course on digital circuits. I mean, you actually get to build different logic gates, like being in a lab, and rediscover how they are at the heart of every computing device. I've been recommending Brilliant to my colleagues, to my students from way before they started sponsoring my videos. So if you want to try everything that Brilliant has to offer for free for a full 30 days, you can go to brilliant.org/FloatHeadPhysics. The link is also in the description, or you can just scan the QR code. And if you use my link to buy a subscription, you'll also get a 20% off. Okay, back to the video. Einstein, this is all amazing and I truly appreciate it, but you still haven't answered my original question. Why use this? I mean, I can always choose to use a square grid and stick to Pythagoras, right? And Einstein says, yes, Mahesh, you're right. When it comes to flat surfaces, you don't need to use these curved coordinates with varying metric. You can just choose to use a flat grid with a constant metric and just stick to Pythagoras. But what if you're dealing with a curved surface like that of the Earth? Now, even if you try to put the simplest grid, like latitude and longitude lines, look, now the distance, the unit keeps changing. So you have no choice but to deal with varying metric. It's impossible to find a grid where the metric stays the same everywhere. That's just not possible. Which means you are forced to use this general formula to calculating distances over here. But wait a second. I can draw a map and put a square grid on it, right? Yes, says Einstein, but you can never, ever make the metric a constant. This is impossible. Whenever you do look at maps, the metric keeps varying one way or the other. That's why all world maps are distorted, because you're forced to have a varying metric. It is impossible to draw a world map which has a constant metric. It's not possible because the intrinsic geometry itself is curved. Okay, so what does it all mean now? And Einstein says, and this is the climax now, okay, ready for it? So Einstein says, this means we now have a way to check if a given space is curved or not. If someone gives you a coordinate system with a varying metric, and you want to check whether it's flat or curved, just try to do a coordinate transformation and see if you can find a metric that looks like this, a constant one. If you can, then that means the space is flat. This varying metric was just an artifact of using weird coordinates. But if you find that it's impossible to convert it into a constant metric, regardless of what coordinates you choose, you just cannot transform it, then that means that the varying metric is not just an artifact of coordinates, it is built into the geometry. That means that that space was curved all along. So look, we have a mathematical way to check whether a space is curved or not. Isn't that amazing? And I say that sounds awesome, and I still need some time to wrap my head around it, but why do I ever need it? I mean, why go through all of this trouble? I can always look at a space and tell whether it's flat or curved, right? And Einstein says, not really, Mahesh. I mean, look at a cylinder. It looks curved to you, but you can put a grid with a constant metric because you can literally open up a cylinder. So in that sense, it is flat. So you cannot, it's not that intuitive. But more importantly, your intuition only works for two-dimensional surfaces. But this mathematical tool that we have, that works for any number of dimensions. That means we have a method, at least in principle, to check whether a 10-dimensional abstract space is flat or curved. From Pythagoras to the ability to check flatness and curvature of n-dimensional surfaces. I don't know about you, but that is insane. I mean, tell me that is not insane. But what Einstein does next is even more insane. Einstein says, if we can apply this to n dimensions, can we just apply it to 4-dimensional space-time? This was the big leap that Einstein had. I mean, this idea of metric and curvature and all of this existed way before Einstein, but people only applied it to space because time was an independent universal thing. Until special relativity came along, Einstein showed that it's much better to model our universe not as 3 dimensions of space plus time, but 4-dimensional space-time. And so now we're about to discover how to take this idea to its full potential. Are you ready? Let's jump to space-time. So instead of two houses, which are very close to each other, let's consider two planets far away. So over here, both axes are space. But if you want to jump to space-time, we want to consider one axis to be space and the other to be time. So now we have space and time. Now, when we only consider space, what matters to us is physical distance between things. For example, the distance between planets. Let's say these two planets are 4 light years apart. But when it comes to space-time, what's important for us is distance between events. That's what matters. So let's consider an event. Let's imagine there's a spaceship that moves from here to here at a constant velocity. So our first event would be the spaceship leaving this planet. So let's put that over here at time t equals 0. And let's say the spaceship goes from here to here at a constant velocity and arrives over here 5 years later. So that is the second event. So the spaceship arrives over here and this is event 2. And notice the event 2 is 5 years apart in time. The central mind-boggling thing about relativity is that just like how when you think about distances between two objects, like the two houses, the horizontal and the vertical values are arbitrary. They depend on, which coordinate system you use. They change, isn't it? What doesn't change is this actual physical distance. In a similar way, in space-time, the space and time between events are also arbitrary, which means there could be another observer moving with respect to us, and he will disagree with these values. He might say something like, hey, the space between events is just 1.5 light years, and the spaceship only traveled for 3.5 years, and we are both right. Space and time between events are arbitrary. They are not real things. They depend on reference frames. But even though people disagree on horizontal and vertical, they all agree on this physical distance given by this formula, the Pythagoras. In a similar way, even though people disagree with space and time between events, they will all agree, everybody will agree on the space-time distance or space-time interval between events. And how do you calculate that? Well, you calculate very similar to this, except you have a minus sign. And at first I'm like, wait a second, where does that minus sign even come from? Like, you're just throwing that formula at my face. And Einstein says, actually, there's a very elegant way to even rediscover this idea. But that's a story for another video because it comes from special relativity and the fact that, we all move at the speed of light through space-time, all of that stuff. Nothing to do with metric and stuff. This is special relativity. So let me know if you want to dig deeper into what that minus sign is. Where does it come from? That's also pretty cool. But for the sake of this video, what's important to understand is that if you now plug in the values 5 square minus 3 square, we get this to be 3. And the same value we'll get if you plug in 3.5 and 1.8. In other words, every single observer in this universe will agree that the space-time interval between these two events is 3 units. That is invariant. Everyone agrees on it. But wait a second, what exactly is this 3 units? How do I think about it? And Einstein says, again, we can rediscover these ideas ourselves, and we'll do that in a separate video. But this term happens to be proper time, which means it's the amount, it tells us how much an object has aged when it has gone from one part, one event to another. So in other words, the inhabitants of this spaceship only aged by 3 years. So even though we saw the spaceship take 5 years to go from here to here, the inhabitants only aged by 3 years. This is time dilation. But what's important is that everybody agrees, even the other observer will agree, that the folks in the spaceship only aged by 3 years. That is something that's invariant, and that's why we call it the proper time, because everybody agrees on that. So long story short, the distance formula here tells you, well, how much is the distance between two objects, right? But the distance formula over here, Mahesh, it tells you how much an object has aged when it goes from one event to another. Very different things, but still look at the formula. They are so similar, which means we can draw a parallel between these two. Just like over here, we can say that the metric is a constant. I can now put a grid over here and say the metric over here is also a constant. But of course, the small difference is that there is a minus sign because there's a minus sign in my formula, but everything else remains exactly the same. By the way, we give this metric a name. We call it the Minkowski metric. It's named after Einstein's professor, who he didn't like very much. Now, of course, this is just the two-dimensional version of the metric where we have one dimension of time and only one dimension for space. Of course, we live in 4 dimensions, so this is the full Minkowski metric. And again, the minus sign captures how space behaves differently than time. And yes, you can make the time negative and space positive. It doesn't matter. It's just a convention. But the point is, just like before, when you had a constant metric, we said the space is flat. Now, because we have a constant metric, we can say the space-time is flat. And just like before, you are free to choose whatever coordinates you want. And if you choose weird coordinates, you'll end up with weird metric. But you can always coordinate transform it back to Minkowski metric. That's what it means to be flat. This varying metric was just an artifact of choosing weird coordinates. However, Mahesh, what if you find yourself in a space-time with varying metric, which you can never transform back to Minkowski? Then that means this varying metric is no longer an artifact of weird coordinates. It is intrinsic to space-time geometry. It is intrinsically curved. This is how you can think about space-time being flat and curved. And I find this amazing and really amazing because till now I used to think of space-time as flat and curved only using an analogy, the 2D analogy of flat and curved. But now my thinking has been upgraded. We can now think rigorously. Space-time is flat if you can get the Minkowski metric. If you can never transform it back to Minkowski, it's curved. That is insane. But remember, curved space-time is gravity, which is now encoded by metric. In other words, it's the metric tensor that encodes gravity. It encodes the space-time geometry in it. Wow. But of course, the obvious ultimate question for us now is, how do you actually do this? What operation can you do on a given metric to check whether it can be turned into Minkowski or not? In other words, what operation should you do on a metric to check whether you're in flat space-time or not? And Einstein says that's the ultimate question, and that's something we should dig deeper in a separate video. And by the way, he did struggle with it a lot. But fortunately, he had an amazing friend, Marcel Grossman, who was a brilliant mathematician. So they collaborated together and they figured it all out. Einstein realized exactly what are the different operations you need to do. It turns out you need to do some calculus on the metric tensor. And they figured it all out. And eventually, Einstein was able to encode all of this in his famous field equations. It inputs mass and energy distribution in space-time, and then it outputs, after a lot of work, if you're lucky, it'll output the metric. And this metric encodes the geometry of space-time. It encodes curvature. And when you compute the metric for a simple point mass, you'll notice that the metric blows up at a couple of spots. You could dismiss that as a weird mathematical glitch, or take it seriously, dig deeper, and discover event horizons and black holes. That's literally how we did it. And if you set the proper time to 0, you get the path that light takes. It's called the null path. Einstein used exactly this to predict how starlight would bend near the sun. And during the 1919 solar eclipse, Eddington measured it and gave the world the first direct confirmation of general relativity. It's the same math we use to simulate these black holes as well. And if you do a bit of calculus on the metric tensor, you can figure out the free fall paths, the orbits, the geodesics. Einstein did this and realized that planetary orbits should actually precess slightly, and it perfectly accounted for the Mercury's orbital precession. And because this equation gives you proper time, you can use it to compute how fast clock ticks at different altitudes. That's exactly what's needed to correct GPS systems. Without it, they would be off by kilometers every single day. But that's not all. You may even wonder, can the metric vary with time? Could it oscillate? Well, then you would hypothesize gravitational waves. And if the metric changes continuously with time, then you can hypothesize the expansion of the universe itself and even predict the Big Bang. The metric is the heart of general relativity. We'll dig deep into all of these soon. See you.